The integral as a net change. Objectives. By the end of this lesson, you should be able to set up integrals that solve net change problems in a variety of settings, and evaluate integrals analytically and with the use of a graphing calculator. Alright, so this section is called the integral as a net change, and what that really means is that we're finally going to start using integrals to solve application problems, so word problems. And at the very beginning of this chapter, when we started talking about finding area under curves, the very first thing I did was I said, well, why area? Why are we even studying this? And I really went over a quick example of the fact that an integral represents net change. So just to kind of redraw that for a quick second, I drew a velocity function. I said, well, what if this represents a velocity function? And we were asked to find how far the object traveled between some time A and some time B. And it turned out that when we found the area under the curve and between the x-axis, that number, that quantity, ended up being the total distance traveled. So when I took the integral of a rate, because now we have that terminology. At the very beginning, we were just asking ourselves, how do we find this area? Well, now we know that to find an area under the curve, we're really setting up a definite integral. And the answer to that integral, in the case of a velocity function being the integrand, well, that ended up giving us a total distance traveled. So we're going to end up going back to that idea, and we're going to explore taking the integral of different rates in general. So velocity is an example of a rate, but we're going to look at rates in other contexts and solve multiple application problems. So we want to use integrals and the area interpretation as a way of computing net change or total change. So one example is to find total distance traveled. And again, that was the example we kind of led this whole chapter off with. So a little more formally, the net change is the integral of a rate. So the net change in s of t, and s of t we're used to thinking of it as a position function, but I also want to think of it as accumulating a quantity. So the net change in this position function over some interval of time, so these are going to be real world problems where they're functions of time, so over some interval time 0 to time 1, so an initial time to an ending time, is given by the integral from t0 to t1 of s prime of t dt equals s of t1 minus s of t0. So here we have the derivative of this position function. So when we take the integral of a derivative, so we're choosing to write s prime of t, not v of t, because I don't want to be tied down to the fact that s is this position that always has to do with maybe a particle traveling along a line or a car traveling along a straight line. I want to think of s of t as some position or quantity function. The rate at which either the object is moving or the rate at which we're accumulating something is the derivative. So when I integrate a derivative, the Fundamental Theorem of Calculus Part 1 says I get back to my original function s evaluated at the upper and then lower limit of integration, and then we subtract those. So this is a restatement of the Fundamental Theorem Part 1, but it's given in context of a type of problem. So the net change, how much something has changed, whether the change in position would be distance or a change in quantity would be some amount, is given by the setup of this integral here. So just a couple of things. The first note is that rate will not always be given using derivative notation. So a problem may not come right out and say the rate of change is given by f prime of t, or they may not use that prime notation. They may not even use the dy dx notation, but they will tell you in words that you've been given a rate of change. So cars have been traveling or the car has traveled at a rate of 5 feet per second. So by now you should be able to recognize a rate that's been given as a unit of a distance over a time. And then we will often use the formula given above in a different way. So this formula right here is a rearrangement of this one up here. So what I've done here is I've went ahead and added the s of t0 off to the other side. That's the only rearrangement. So s of t0, the initial starting point, plus here the net change is going to get us to the final point. So that's a really good way to think about it. So S of t0 being my initial time, so my initial position plus my change in position is going to get me to the final position. So it's a really great way to think about this rearrangement. And oftentimes we're asked to solve problems using this rearrangement instead of this original equation. Alright, and now we're just going to go ahead and jump into some examples. So what I will say is that a lot of these integrals, I'm going to go ahead and set them up because that's the most challenging part, is setting up the integral. And then a lot of the calculations, I'm going to have us just work through on the graphing calculator, or I may just provide you the answer. So in this lesson, I want to focus on the setup more than solving the calculations because we've already gone through so many chapters of evaluating integrals. So now it's about setting them up. So in this example, the number of cars per hour passing an observation point along a highway is called the rate of traffic flow, Q of t, in cars per hour. Part A. Which quantity is represented by the integral from time 0 to time 1 of Q of t dt? So this is asking you to write out more of a sentence answer to say that we understand what is meant by evaluating this integral. So let's go back and read the problem. The number of cars per hour passing an observation point along a highway is called the rate of traffic flow Q of t. So I've been given a rate of change, I've been given a derivative. Even though I haven't been given it in prime notation, I've been given a derivative. And the rate of change, the units are in cars per hour. So if I want to think about how to explain what this integral represents, a really good way to think about it at this point is to draw a graph. So just a rough sketch, let's say I have this function Q of t, and I'm just going to say it's a horizontal line to make it really easy. So this is my rate of traffic flow, and the units of Q of t are in cars per hour. So on the vertical axis, we have cars per hour. And on the horizontal axis, which is the time axis, I'm going to have a units of hour. So now if I want to think about an integral from some time 0 to some time 1, well, we now understand that an integral, a definite integral, is the area under a curve. So in this case, because I made it a horizontal line, this area is a rectangle. And I want to think about, well, what does this represent in terms of the rate of change I've been given? Well, the area of this rectangle, the base, the units of the base is in hours. The units of the height is in cars per hour. So if I multiply base times height, I'm going to have hours times cars per hour. So what's going to cancel when I find the area? The units of time, hours, and I'm left with cars, the number of cars. So what quantity is represented here is the total number of cars that's going to pass through or pass by this observation point on the time interval from time 0 to time 1. So let's go ahead and erase this, and we want to summarize this in a sentence answer here. So the rate we were given is in cars per hour, and my units of time were in hours. So the idea is that the units of cars is going, or the units of hours, the time is going to cancel, and we're only left with a unit of cars. So this integral represents the total number of cars that pass the observation point on the time interval, or between time 0 and time 1. So counting how many cars pass by. So this is the rate at which they pass by. So in cars per hour, so at any particular moment, we can plug a time in hours into this Q of t function and find out that at that particular moment, 20 cars per hour are passing. But this integral of the rate tells me exactly how many cars went through the observation point over a particular time interval. So in other words, we got a net change, or a quantity, out by taking the integral of a rate, because Q of t here is a rate, even though it doesn't have the prime notation. Alright, so now I want to move on to part B. The flow rate is recorded at 15-minute intervals between 7 and 9 a.m. estimate the number of cars using the highway during this 2-hour period by taking the average of the left and right endpoint approximations. So I'm being asked to estimate the number of cars that use the highway, and we can figure that out by figuring out how many cars pass by the observation point during this 2-hour period. So part A, we decided that to find the number of cars that pass by, we were going to set up an integral. So it's going to be the integral over the time frame. So here the time frame is from 7 to 9 a.m. So I'm going to set up the integral from 7 to 9 of the rate function. So the rate function is still q of t dt. So this is what I'm aiming to find. But I wasn't given q of t explicitly, so I don't know exactly what this function is. I only have snapshots of information at 15-minute intervals here. So I'm going to approximate this, and they're telling me exactly how to approximate it. They're telling me to take the average of the left and right endpoint approximations. So here, what I want to do is I want to find a left and right endpoint approximation, add those two together, and divide by 2. That's how I find an average. So let's figure out how many rectangles to use. So here, between 7 and 7:15 is one rectangle. Here's the second, third, fourth, fifth, sixth, 7, and 8. So I want to use 8 rectangles, so I'm going to try to find L8, and I'm going to try to find R8, and then I'm going to divide that by 2. I'm hoping this jumps out to you as the same thing as T8. So remember that an average of the left and right endpoint approximations is the exact same thing as the trapezoidal approximation. So since I have this knowledge, let's go ahead and use it so that I don't have to compute 2 separate left and right endpoint approximations. So I'm going to instead evaluate T8. So the way we find trapezoidal approximations, if you remember, is we double all of the middle function values and we leave the 2 endpoints the same. But we have to make sure and include the 1/2. We have to make sure and include the delta x. So the delta x is going to be the change in x, or really the width of each of the trapezoids, or the height, because the height falls along the x-axis. But here's where I want to be careful. I don't want to use 15 because my units are in hours. So here 15 minutes is what fraction of an hour. So if I'm thinking about 15 minutes, it's 1/4 of an hour. So it's going to be 1/2 delta x, and delta x is 1/4. And then here's where I leave the first output alone, and then I start to double every middle output. So 2 times 1,297, 2 times 1,478, and so on. Oops, 44, plus 2 times 1,451, plus 2 times 1,378, plus 2 times 1,155, plus 2 times 802, plus, and we don't double the last term, 542. And plugging this into our calculator, we get 2,549.5. But we don't want to leave our answer as half a car, and we are estimating, so we'll say 2,550 cars use the highway between 7 and 9 a.m. Alright, let's take a look at another example. So a survey shows that a mayoral candidate is gaining votes at a rate of 2,000 T plus 1,000 votes per hour, where T is the number of hours since voting began at 7 a.m. How many votes will the candidate have at the end of the voting period at 8 p.m., assuming that at time t equals 0, she had 30,000 absentee ballots? Alright, so the question we're being asked to find is how many votes will the candidate have? So the emphasis on how many, the emphasis on that we're looking for a quantity. And we've been given a function that's a rate. So the candidate is gaining votes at a rate of 2,000 T plus 1,000 votes per hour. So this is a rate of a quantity over a time, so votes per hour. So what I want to do is set up an integral. So I'm going to set up an integral from a starting time to an ending time of a rate, and that rate was given as 2000 t plus 1000 dt. So now the question is, what are my limits of integration? So here I want to be careful. I don't actually want to put 7 down as my starting time. I actually want to start recording at some time 0. So the time here, I'm going to start recording at time 0. So we're going to say time 0 corresponds to 7 a.m. when votes start to be collected. And then the ending time is 8 p.m. So I want to count exactly how many hours later that is. So it wouldn't make sense to write from 7 to 8. Right? That wouldn't really make sense if I were trying to figure out how many hours had passed because of the whole AM, PM idea. So if I say I'm starting to record at time 0, and time is an hour, so how many hours later is this? So if I start recording at 7 a.m. and I have to be done by 8 p.m., then I'm going to have a total of 13 hours that have passed. So that's going to be my ending time. So between 0 and 13 hours, this candidate is gaining votes at this rate of 2000 t plus 1000 votes per hour. So here, this is the total number of votes that he or she has gained between 7 a.m. and 8 p.m. But they're telling us here that at time 0, she already had 30,000 absentee ballots. So what I'm going to have to do here is I'm going to have to add whatever the output is of this integral. I'm going to have to add 30,000 ballots to that quantity to find that total quantity she has, or he or she has, at the very end at 8 p.m. So this is that alternate variation of the net change formula. So the way we had it written was that s of t0 plus the integral from t0 to t1 of s prime of t dt gave us s of t1. So what I'm in search of is s of t1. How many votes did he or she end up with? So I needed to add how many I started with, that's s of t0, and then I needed to figure out how many were being added on. So now, if we evaluate this integral, I get 182,000 votes plus the 30,000 absentee ballots, which is a total of 212,000 votes. And that there is my final answer. Alright, so we did start off the chapter talking about being given a velocity function, and often we will be given the rate as a velocity function and asked to find either displacement or total distance. So if an object is traveling in a straight line with a velocity function v of t, then the displacement during the time frame between t0 and t1 is given by the integral from t0 to t1 of the velocity function v of t dt. And the total distance traveled over the time interval from t0 to t1 is the integral from t0 to t1 of the absolute value of v of t dt. So let's just talk real quick about what's happening here. So let's say I have a velocity function, and let's make it linear. Let's say it looks something like this. So here's my velocity function. Now, if I want to know the total displacement, so let's say this is t0 and this is t1, and I want to find the displacement. Remember what that means. So if we're traveling along a straight line, so here's my straight line, and let's say this is my starting point. And I start traveling with a positive velocity. So let's say I start traveling to the right, and then I stop, and then I end up having negative velocity, and then I start going to the left. And I want to find my displacement. Well, if you remember, displacement is how far away you are from your starting point. So how far away I am from my starting point, if I started out going right and then stopped, turned back to go left, let's say this little quantity here is 3. Well, distance traveled, if you remember, means I need to add up all the different units that I traveled. So I traveled to the right, let's say this measurement was 3 units, then I stopped and went all the way back. So now if I'm thinking about how much gas I've used, I don't care about the displacement, because every day I start out at home, I drive to school and go back, my displacement is 0. But I sure definitely use gas because I did travel all the way to school and all the way back. So here my distance would be 3, and then I have to go back 6, so I have a distance of 9. So remember that relationship, that distance is always going to be greater than or equal to displacement. Now, if I'm thinking about it in terms of integrals now, let's say this is my velocity function. If I'm interested in finding displacement, well, that's going to be the integral from time 0 to time 1 of the velocity function. So here, let's use a different color. So let's go ahead and shade in the region we're interested in. All of this area below here would be considered negative area, and then all of a sudden we'd start accumulating some positive area here. And so we'd have negative area and positive area. It looks almost exactly the same, so it looks like in this case our displacement would be 0. So I travel to school and then I travel back home again. But if I'm considering total distance traveled, now what I need to do is I need to look at the absolute value of the function. So v of t here is the red function, but the absolute value of v of t means that I take any portion of the graph that's below the x-axis and I make it positive by reflecting it over the x-axis. So this line down here moves up, and then this portion of the graph stays the same. It's already above the x-axis. So now I'm trying to find all of this area here and all of this area here and add it together. So it's going to be a positive quantity. It's not going to be 0 anymore. So that's the same as I could have found all this negative area and then just made it positive and then added it to this portion over here. So keep this in mind as we go on and do some applications of this. Alright, so here we're given a velocity function. So the velocity of a particle is given by v of t equals t cubed minus 10t squared plus 24t in feet per second. So first we're being asked to find the displacement over the interval from 0 to 6 seconds. So here I want to focus on the setups of each of these problems. So if I'm looking for displacement over the time from 0 to 6 seconds, the integral I'm setting up is the integral from 0 to 6 of a velocity function. So t cubed minus 10t squared plus 24t dt. So the answer here is going to give me the total displacement of the particle between 0 and 6 seconds, and the answer here ends up being 36. So thinking about our units here, we wanted to find displacement, so my units need to be in feet. So the total displacement of the particle between 0 and 6 seconds was given by this integral, which if we solved it, we would get 36 feet. Now, the difference in part B is that I'm being asked to find the total distance traveled. So here I want to make sure that I'm considering if any part of the function goes below the x-axis on the interval from 0 to 6. And the question becomes, how do I know that? Do you know how to graph t cubed minus 10t squared plus 24t? Well, the nice thing is that we don't need to know explicitly how to graph this thing. I'm going to graph it just to show exactly what's going on here. So a rough sketch of the graph in the region we're concerned with, so between 0 and 6, what it's going to look like is it's going to look something like this. So this is 6 here, and then this point here, we're going to find it, so I'm going to leave it blank, and then this one here is 0. So we're interested in finding the total distance traveled. So we just found displacement. So what we found is we found all of this area up here, which is positive. We subtracted from it this area down here to get the total displacement. So to get the total distance, well, what I need to do is I need to add all of this area here, and then this area here that would be considered to be negative, I need to make it positive. But now, how do I do that? It's a little bit easier when I have a graph and it's all lines and I can just flip the line over. So ideally, I'd want to try to do this and flip this portion over. But there's a different way. And here's what we're going to do. If we can find this point here, so if we can find this x value, what we can do is we can break up the integral into two separate integrals. So the integral from 0 to this point here plus the integral from this point here to 6. So I want to find this, the integral from 0 to 6 of the absolute value of the velocity function. So t cubed minus 10t squared plus 24t. That's what I want. But, I can't just drop the absolute value bars. It doesn't work like that. So what I have to do instead is I want to write this as two separate integrals. So I need to find any place where this function here is equal to 0. Because if this function, so here's my function v of t, if this function is ever equal to 0, then it either touches the x-axis and then bounces off of it, or it crosses the x-axis, and that's where I may potentially have negative area. So what I need to do is I need to be safe about it. I need to find any place where this velocity function, v of t, equals 0. And I find those places, those t values where this happens, and I break up this integral into separate integrals using that time value. So I want to find the integral from 0 to that number of t cubed minus 10t squared plus 24t dt. So now I can remove the absolute value bars and leave it as parentheses, but how do I know that this portion between 0 and whatever this number is going to be, how do I know that that was above the x-axis? You only know because I drew the graph for you. Well, what happens if it was below the x-axis? Well, the point is that even if it is below the x-axis, what would we do? We would just make it positive. So how do you make something positive? You put absolute value bars around it. So we're going to change this problem to two separate integrals, and we're going to move the absolute value bars to the outside of the integral. And then we're going to add a separate integral from whatever this value is to 6 of the same function, t cubed minus 10t squared plus 24t dt. And we're going to put that quantity in absolute value bars. So we know, because we've drawn the graph, that we're going to have to make this portion, we're going to have to force it to be positive and live up here. But because in general we wouldn't normally know what the graph looks like, we just have to make both quantities positive no matter what and add them together. So now, how do we find this value? That's the value we're really looking for here. So to find this value, or even the value of 6 for that matter, or no, because this was the interval given from 0 to 6, sorry about that, but you'll see why 6 is important too in just a second. If we set the velocity function equal to 0, we're searching for the zeros, so the x-intercept. So we're going to set t cubed minus 10t squared plus 24t equal to 0. Well, t is common in everything, so we'll factor out a t. We're left with t squared minus 10t plus 24 equals 0. So t equals 0 is one x-intercept. And now I want to go ahead and factor this other portion here. So I jumped ahead a little bit. So I have t, and I want to factor this, and this is going to factor to t minus 6, and then t minus 4 equals 0. So I'm going to have t equals 0, t equals 4, and t equals 6 as the zeros of my function. Well, I already knew I had to stop at 6 no matter what, because that was the interval that I was given to look at the total distance traveled over. But 6 happens to be a 0. So the value that I was searching for here is 4. So any point where the velocity is 0, any time, that's one of the times I have to break up the integral. So we may need to break up the integral into more than 2 integrals, or even 3 or 4, depending on how many times the particle stops between 0 and 6 seconds. So now the point that we're going to fill in here, the time, is 4. And so we're going to solve each of these independently. This first one here, we know is going to be a positive number, but we only know because we knew what the graph would look like, so we have to keep the absolute value bars. And it turns out that we're going to get that this first part ends up being 128 over 3 plus, and now the second part, because we knew what the graph looked like, this part's going to be negative. So this would be negative 20 over 3. But now what's going to happen is the absolute value bars will make both positive. So plus 20 over 3. So I get 148 divided by 3. And now if I add these, or if I simplify this, I end up getting, if I want to, this is my exact answer, but if I want to leave it as a decimal or write it as a decimal, it's going to be 49.333 repeating. So the reason why I did that, and I have to include my units of feet, are because I just wanted to make sure that this distance, we knew, because we knew the graph had to be more than 36. So quick sketch of the graph again. We went way up here and had positive area, and then displacement means that this area stayed negative, but when I did the distance, this portion up here became positive, so now I was adding all this part here. So I wanted to make sure 148 over 3 as a decimal was a bigger quantity than the displacement, because I did know what the graph looked like, but in general we may not know.